Now let me tell you guys how to use ordered n tuples to start talking about Turing machines. So our objective is to find a number that codes a Turing machine. So the trick I just described can be used to define a formula tuple, which is true just in case x1 is an x2 tuple. So in other words, it codes up a sequence with x2 places, of which the x3th member is x4. So you could say something like, that guy codes a 5 tuple, of which the third element is 17. So we now have that amongst our defined bits of vocabulary. OK, and now what we want to do is start using numbers to code up Turing machines. So the first step is to use numbers to code up the programs for Turing machines. And we can definitely do that, because thanks to that predicate, we can use a number, say, n, to code up some finite set of numbers, say p1 to pk. And then we can let each of these code up a tuple, which is just one Turing machine instruction. So for example, maybe p1 codes up 0, 1, 0, right, 7. Of course, right isn't really a number, but that's no problem, because we could just think of right as 1 and left as 2 and don't move as 3. So in effect, each member of this sequence codes up a line of our Turing program. So the entire sequence codes up the entire program. And it's relatively easy, though long and boring, to use this vocabulary to just define a predicate, which in effect checks that it's not just a random sequence, that it really is a sequence that corresponds to a well-formed program. So you check that each of these is a 5 tuple, of which the first element is, well, that one can be anything you want. These two need to be either 0 or 1. That one needs to be 1, 2, or 3. That can be anything you want, and so forth. OK, so now we can use natural numbers to code Turing programs.